Do you remember as a kid going to the restaurant and you had the kids menu, and on it might have had two pictures that looked very similar, and they asked you spot all the differences, right? You're supposed to look very closely at the pictures and see if you can see a difference. Well, look at the right and look at the left picture here. Could you spot the differences? Well, in this case, you shouldn't be able to spot any differences. It's the same photo. But that begs the question, how different is the surface of Mars today compared to 1,000 or 100,000 years or a million years ago? This photo was snapped by the Curiosity rover, which has spent many years trekking across an ancient lake bed inside the large crater on Mars. It's a barren, forbidding, but strangely familiar and, I would say, beautiful scene. Look out across this cold and dry landscape. One might wonder, if this was once a lake, how long ago was it that water filled this crater? When did the water disappear, and how long did it take for the sediments that were laid down in the lake to erode to the exact point that we're witnessing them today? To address those broad questions, let me first address a more specific question. What if you had been walking on Mars, say, 6,000 years ago, at this very spot that the Curiosity rover was positioned when it took this picture? What do you think that you would have seen? What differences do you think you would have spotted between the photo taken at that time and the one taken presently, this one you're looking at right now? If you look at the amazing textures in this particular rock outcrop, you can tell that there's some kind of complex sort of pattern of erosion that's taken place. There's these little thin slabs of rock projecting into the very thin Martian air. Some of these little thin slabs are well less than an inch, just sometimes millimeters thick. Considering the following question, how far into the future or past would you have to travel in order for you to spot any difference with what we observe today? We're asking a very fundamental question about what the rate of erosion is on the surface of Mars. Scientists that study Mars have provided evidence that if you were to take this picture and set it next to a picture taken at the same position 6,000 years ago, you would have a lot of difficulty distinguishing any real obvious difference between the two. But what makes scientists confident? There's so little that has happened on Mars for thousands of years. The Curiosity rover has provided, through some really clever methods, the very first estimates of both the age of some Martian rocks and the actual pace of erosion those rocks have experienced over time. What does Curiosity determine about how fast rocks at this location of Mars have been eroding for the past, say, 6,000 or 10,000 years, or even millions of years? Data obtained by the Curiosity rover allows us to estimate that these rocks are eroding at about a half inch per 1,000 years. Let me say that again. Just 1/2 inch of the surface of the rocks, the exposed rock surface of Mars, is being eroded over 1,000 years. So to erode just 1 foot of rock, as we see in this picture here, would require potentially 24,000 years under the current environmental conditions. All right, look, it's the environmental conditions on the surface of Mars that causes such low rates of erosion. The only erosive forces active at this particular location are winds that are laden with dust, but let's face it, it's a very thin atmosphere, which means it can't pick up very large dust particles, so they're very small particles moving through the air. There's thermal contraction and expansion, right? Heating and cooling, so the rocks are expanding and contracting, and that can cause them to crack and break and eventually loosen, and that's going to cause some erosion. There's also a bombardment by high energy cosmic radiation that is literally breaking down the surface of the planet itself, but at a very slow pace. There's actual chemical degradation by chemical processes via the molecules that are in the rocks themselves. Now, look, none of these forces can act very quickly in the very thin, cold atmosphere of Mars, which is devoid of any chemically active molecules. Under present conditions, measured directly by the Curiosity rover, right? We have an instrument that's on the face of Mars that is measuring many different conditions there. Erosion of 1/2 inch per 1,000 years seems almost too good to be true. It seems like a fairly high pace considering how difficult it would be to erode the surface. Nonetheless, these rates of erosion suggest that the spectacular geological features observed in the Gale crater, which is where the Curiosity rover resides, haven't changed much in hundreds and thousands, if not millions of years. This very slow pace of change on the surface of Mars is really powerful evidence that the Mars surface is very ancient. In fact, it's far older than the surface of the Earth, which the Earth has a much more dynamic surface. There's a lot of erosion occurring, and that eroded material is being replaced by tectonic forces, which are uplifting sediments into mountain ranges, which then allow more erosion to continue. Now let's take a little diversion here, and let's ask about this Mars geology in the context of young Earth creationism, or I'll call it young Mars creationism in this case. So many literal six-day creationists believe that not only the Earth is a mere 6,000 years old, but the entire universe, and therefore Mars as being part of the universe, must only be a few thousand years as well. For them, the features of Mars present, I'll say, a bit of a conundrum, or a big question. If Mars is only 6,000 years old, and we were to go back in time and take a photo of the planet on the day of its birth, the day of its creation, would it look completely different? Or would we have difficulty spotting any differences? Most young Earth creationists believe that Mars could not really have appeared as it does today because, after all, they believe that the great scars or the craters that are on its surface and the evidence of volcanism and so forth, that couldn't be part of a perfect original creation. Therefore, they believe that it once was a really different place with water-filled basins and a thicker atmosphere. And so if it was a really different planet then, it must have undergone a radical transformation. And when did this radical transformation occur? It must not have occurred very long ago. Look, this image right here has lots of evidence of layered rocks, right? It looks like sedimentary rock here. Sedimentary rocks suggest a pattern of erosion that laid down these sediments. But then after the sediments were laid down, they would have had to have lithified, right, become rock. And then you had to have a period of erosion to present them to us in the present condition. Right? When they look at the layered rocks, like in our photo, what's their response? Like, how do they explain this? Well, many propose that Mars must have experienced like a far different conditions in the past, allowing for maybe vastly higher rates of erosion. Yeah, it's possible that conditions in the past were different than they are today in the present. In fact, exogeologists are convinced that Mars indeed experienced an entirely different climate in the past, though they believe that was some 500 million years ago, and it was really different. But would conditions have been radically different only a few thousand years ago? Almost certainly not. The Curiosity rover has provided additional data that confirms that the presently observed conditions in Mars have persisted well into the past, and I will present you with some of that evidence in a future video. Now, faced with this increasing evidence of massive amounts of sedimentary rock, like what's staring you in the face here, what would what we'd call young Earth or young Mars creationists, what would they do? Well, they're quickly adopting a catastrophic recent origin of those geological features, just like they have on Earth. They accept the satellite and rover gathered evidence that water once flowed all over the surface of Mars. They can see that there's massive deposits of sedimentary rock. They can see that there are erosion features that suggest large rivers, and they can see shallow areas that have rock types that are evidence that there were shallow seas or large lakes. So for one type of response, let's look at an example from Answers in Genesis and Andrew Snelling from 2007. Here, Snelling, in an article entitled Water Activity on Mars, Landscapes and Sedimentary Strata, Andrew Snelling says, there is no longer any doubt that the surface of Mars has been in the past covered by huge volumes of water which spread over vast areas. These resulted from cataclysmic outflows, which were also responsible for catastrophic erosion of channels and valleys on a scale far greater than anything comparable on Earth, and deposition of sedimentary strata. Now, I've written and talked about Snelling's opinion on this in an earlier video. The global flood of Mars, like where did the water go? This whole idea that there was a catastrophe on Mars just like there was on Earth. You see, young Mars creationists recognize that the current rates of deposition and erosion, they can't explain the present day observations of the features of Mars. So they just have to invoke some sort of catastrophic past. But you might be saying to yourself, wait, Why not simply invoke supernatural or special creation? Why not say that God just created Mars, right? To look just like what the Curiosity rover is showing us today. This is known as the appearance of age hypothesis. And young Mars creationists, I think, rightly resist claiming that God simply created all this evidence of a past history of Mars, because that's what you're looking at in these pictures is, sedimentary rock is a record of history, of a series of events. Erosion is a record of events and history. But of course, young Earth creationists, young Mars creationists, they're bound to an origins view that requires Mars be a very young place. And therefore, that forces them to find some alternative explanation for the evidence of the massive changes that are pretty obvious to their eyes. So therefore, the appeal to a Noahic-like catastrophic condition that was in the fairly recent past, like 4,500 years ago. So while it's agreed upon by all geologists that past conditions were different in the past compared to the present for Mars today. However, there's no evidence to support the conjecture that the conditions have been significantly different in the very recent past, like in the last 100,000 years, right? There's craters filled with sediments that are then eroded, that have valleys, and there's craters that have craters inside of them that show less erosion and other craters that show more erosion. There's a whole continuum of different observations of different histories on the surface of Mars. See, the conditions that allow for the unique appearance of the rock formations that the rover is examining today are clearly the product of long exposures to wind erosion. And I'll have many more pictures of Mars in my next video that demonstrate this. How long? How long does that erosion take place? Probably hundreds of millions of years of erosion at the rate similar to what we're observing today is necessary to account for some of the geological formations that we observe. Now, I do want to make one last observation. One last, I guess I would say, challenge to the young Earth creation view or young Mars creation view of the history of Mars. And that is that I would say that I don't think that I'll present another evidence that Mars hasn't changed much over the last many thousands of years. You see, I know that Mars has been called the red planet for at least 4,000 years, right? The very fact that it has been observed to be red, right? Ancient Egyptians called this the red planet. They've been observing the planet for a long period of time, and it appears red in the night sky. The very fact that it's observed to be red for this long tells us that the planet has been devoid of water, and it's been covered in red dust for at least that long. That's why it appears red. So wind erosion has been the only significant game in town with respect to erosion for that period of time. I mean, if there had been a huge flood just 4,500 years ago, 500 years before the first recorded observation of the red planet in the sky, right? If that had happened, if there had been a great flood 4,500 years ago on Mars, just like on Earth, then there would have been massive amounts of water vapor in the atmosphere following that flood, right? The planet wouldn't have looked red to the ancients. It would take thousands of years for that water that covered the surface of Mars to dissipate out into outer space, right? Not thousands, right? Tens and hundreds of thousands of years. It would take a while to transform that planet into the barren, dry place that it is today. So it appears that the red planet has been a dry, barren place for at least as long as people have looked up into the sky and wondered about the history of Mars. In my mind, observations that we make on planets like Mars are as big, if not a bigger challenge to young Earth creationists who want to hold to an entire universe age of less than 10,000 years, actually about 6,000 years. Anyway, that's my challenge for today. To ask oneself, how different will this image be 10 years from now, 100 years from now, 1,000 years from now, would you expect any changes at all? And to think about the past. How did we get to this particular point? What forces would you bring into play to suggest that the amount of erosion seen just in this image alone, I don't know if you can tell, but in the background there's some hills, which are actually several thousand feet high. And those hills are full of sedimentary rocks, right? And they're in the center of this crater. And they're thought to have formed from a massive lake that had filled up sediments into this crater. And then since then, wind has been moving across the surface of Mars. And in the crater, it kind of eddies around and it's been carving out the rocks in the crater, forming these, the people who are studying this particular crater think that several hundred, if not 1,000 feet of rock has been exhumed from this crater and then blown off onto the surface of Mars and other places. That is a massive amount of erosion. And if it's all occurring simply by wind in a thin to thin atmosphere that Mars has, as I said before, the observations of Mars are that it's been on the red planet for a long time. That's hundreds of millions of years of erosion at the pace that we measure erosion occurring today. Even young Earth creationists are going to have trouble with their global flood hypothesis, depositing it on Mars. We're inside of a crater. In that crater, yeah, sure, you could see that if there was a giant flood and it filled this crater with water, and there was lots of mud mixed up in that, and it laid down all these layers, great. You have the bottom of the sea, and then you have the evaporation of all that water from this huge lake, which again, I think would take hundreds of years just to evaporate that water, much less having it leave the atmosphere. But then once you had a flat surface, you then had to erode it down. And there are hills, I mean, I'm just showing you one little spot here, but there are hills around this area that are hundreds of feet high. And so that means if it was all of the bottom of a lake at one point, hundreds of feet of sediment have to have been eroded out of the bottom of this crater, exhumed through the action of wind. I mean, you can't use water to erode something that's already at a low point. All right, but wind can do that. So you basically are stuck with wind as an explanation. And just doing some really basic physics will tell you how much material wind can pick up and how much abrasion it can cause, because we have a good idea of what the density of the atmosphere is and the size of particles that can be held in that wind at different speeds, right? Basic physics alone will tell you that you can't form these formations. You can't create the image that you're looking at in front of you right now in the space of just a few thousand years. All right, there you go. Can you spot the difference? I don't think that 1,000 years in the past, 1,000 years in the future, you're going to see anything a whole lot different than what you're looking at right now at this particular location. I'm going to do a couple different videos on Mars. I want to talk about how they determine these erosion rates. We'll talk about actual radiometric dating of rocks that are on Mars that has been done. We're going to talk about craters. I'm going to show you nested craters, craters within craters within craters of different ages. So we're going to talk about the appearance of a series of historical events. We'll look at Mars rover tracks that have been laid down, and now 12 years later, we can by satellite go back and look at them, and guess what? You can still see their tracks, right? Even though they've driven over sand, the tracks are still present and visible. That should tell you a little something about the rate of movement of materials on the surface of Mars in this present time. What else are we going to talk about? I'm going to have potentially a little conversation with a rock sitting on the surface of Mars, and might ask it like how it came to be there and how long it's been sitting there. So we'll pose that question, like how long can a rock sit on the surface before it will experience any real changes during its lifetime? We'll look at a little stratigraphy on Mars, looking at different rock layers. So lots of interesting little things to learn about Mars to sort of complete the picture of the history of Mars and the surface topology. We've got all that coming up when I get to it. Thanks for listening. Hey, we'll talk to you later. Bye bye.